Dear student, good evening. Welcome to the revision class about the introduction to microwave systems and antennas for antennas and microwave engineering subject. So we came to know we are going to learn about the basic principles, then updating or enhancing your knowledge on various antenna designs and knowledge in microwave components and antennas for practical applications. So in the particular class, we are going to discuss about the antenna parameters. First, I can give some recap about the particular subject because that is a very much important. Normally, the RF spectrum spans between 1 to 1000 gigahertz corresponding wavelength from 30 centimeter to 0.03 centimeter for the different applications. It may be a commercial or military sectors. Then last class we came to know physical concept of radiation, how the antenna do the radiation as well as how the antenna radiation can be accomplished. This is the corresponding two-port antenna network equivalent circuit diagram at the source corresponding transmission line and antennas. The important is it's matching from source to the transmission line and transmission lines to antenna. Then the antenna impedance is playing vital role, not only the real term and reactive term also. Now we come to the important thing out of the different classifications of antenna. We'll take that one. Why we need the antenna parameters? Because that's very much indeed to utilize any antenna, or more precisely, we can say if we are taking only antenna for one specific application, how do you know it's going to perform well at the particular application respective frequency? Then the antenna parameters mainly intended to describe the performance of antenna. The particular performance of antenna parameters are defined by IEEE standard 145 document in the year of 1973. That is further refined and finalized in the year of 1983. There are 16 antenna parameters with respect to the input side as well as output side. So the important parameter foremost one is the radiation pattern. From the radiation pattern, correspondingly, it can be extended to the further derived thing: radiation power density, intensity, gain, directivity, antenna effective area, and aperture, beam width, bandwidth, beam efficiency, and antenna radiation efficiency, and then antenna total efficiency, and orientation of the electromagnetic fields or electromagnetic waves within the antenna to the free space communication or free space to the antenna side. It may be in the antenna at the receiver side. Then we have the input impedance, antenna temperature, and gain to temperature ratio. So we will see one by one. First, we can take the first parameter. The parameter is the radiation pattern, because the radiation pattern is very much important, because that is going to defining the mathematical or graphical representation of radiation properties. From the radiation properties only we have the um, field strength, radiation intensity, power flux density, directivity, and polarization. So the particular radiation pattern we can use any one of the coordinate system, RCS, rectangular coordinate system, cylindrical coordinate system, or spherical coordinate system. For the application point of view, for any antenna, we are taking the distance along the two kind of angle. One is called theta and uh, another one is pi. That's called the elevation angle and azimuth angle. So now we can take further detailed information about the radiation pattern. So we can say practically it's a trace of received electric or magnetic field at a constant radiation. So the particular pictorial representation indicating the graph how the spatial variation of power density along the constant radiation. Particular radiation pattern, we can say the desirable radiation. Another one is the undesirable radiation. So in the desirable radiation, we have that major lobe. Then unwanted or undesirable radiation, we can say minor lobe. The minor lobe can be classified again two way. Whatever the lobe just opposite major lobe, we can say minor lobe. Then immediately adjacent to that major lobe, either left hand side or right hand side, we can say the side lobe. But in the particular major lobe, we have the two more parameters. It's called half-hour beam width. Another one is the beam width between first nulls. So half-hour beam width means from the radiation pattern. So we can take from the maximum is 1, means from the half of the power we can take the point on that z axis. Then that point can be extended to both sides. That will cut the major lobe. From that we can find the half hour beam width, followed by the beam width between the first null means. So after that half hour beam width, there is a side lobe. From that we can extend from the point of the maximum, then we can know the what is the first null beam width. But if you know the half hour beam width, then we can easily calculate the first null beam width, or FNBW. The double the time of half hour beam width is first null beam width. So now we can continue further one. The radiation pattern, how it may looks with respect to one of the uh, most widely utilizing antenna, horn antenna. That time we can see how the principal E and H plane patterns for the pyramidal horn antenna may looks with respect to the elevation plane. The time that azimuth angle is 0 degree, correspondingly XZ plane, how it may looks, the electric field distribution, as well as the XY plane. Then azimuth plane is available. We can take that elevation is pi by 2. Then we can see the two-dimensional radiation pattern, how the fields are distributing, then how the wave may propagate from one point to the another point. Then radiation pattern, another one important thing is the field regions, because any antenna can radiate, or the radiation mechanism we came to know, the single wire and two wire. So whenever the charges are accelerated, then that is going to be travel and then can be detached from the antenna. So but the field region point of view, we can take that antenna. This is one of the example for the dipole antenna. The dimension is D. Then whenever there is a particular antenna, we have three kind of radiation region. One is called the reactive near field region. The reactive near field region is immediate to the antenna. For the application point of view or the communication aspect, the reactive near field is not desirable, but it may be a short range communication or long range communication. Then we can have the near field and far field, the radiating field, or we can say the radiating near field or fresnel region, as well as the far field or Fraunhofer region. That is beyond that near field, that can be calculated mathematically from the center position of the dipole antenna to, we have the formula for the distance calculation, how much radiation pattern or the near field reactive, how much area it's covering in the far field, radiating near field or fresnel region beyond that. Then we have the formula is R1 equal to 0.62 into square root of d squared by lambda. So d is the dimension of antenna, then lambda is the which frequency the antenna going to operate. Then we can use a fundamental equation. We can calculate that lambda, as well as the far field or Fraunhofer region. We can calculate this in this formula, R2 equal to 2 into d squared by lambda. So that is a formula we can use. We can calculate the particular antenna, what is the Fresnel region and what is the Fraunhofer region. Not only for the particular the antenna, we can calculate for any antenna. For example, you can take the parabolic reflector. Whatever the radiation is very near to that antenna, that's called reactive. Then the next two are the radiating, how that field distribution may be extending and providing the major lobe. So now we can see another one, two parameters, the radian and the steradian, because that is used in the three-dimensional geometry. The measure of plane angle is the radian, the measure of solid angle is the steradian, but that we can use the conversion with the help of know what is the radian and steradian. That time we can say the one steradian with respect to angle is 180 by 5 whole power 2 degrees. So now we can extend from the out of 16 antenna parameters, we came to know mainly the radiation pattern. From the radiation pattern, important thing is the main lobe, then half hour beamwidth and beamwidth between first nulls. The radiation pattern properties, we have the two things. One is the radiation power density, another one is radiation intensity. So here we can see the radiation power density is how much power radiated by antenna. So we know from the electromagnetic fields basics that is used to describe the power associated with the electromagnetic waves is instantaneous Poynting vector. Or we can say the cross product between the electric field and magnetic field is varying with respect to time. Then we can know how much amount of power radiated by the particular antenna. So that we can mainly calculating the particular radiation power density in the far field regions, and the time that radiation power density predominantly real, that will be the radiation power density. Why we are taking that predominantly real part means then we cannot have or we may can avoid that reactive power. So the continuation we will see in the next class. Thank you.